Okay, so those are our three equations. Now let's use them to derive something in a system like this. Now we're going to make some approximations here to make the maths easier. You can do this calculation without making these approximations, and indeed that's what professionals will do in this field, but it's much messier. So for the purposes of this course, we're going to make the approximations which give us very close to the right answer. And the main approximation we're going to make is that the mass of the star is very much more than the mass of the planet, which is pretty well always true. So it's a good approximation to make. What that means is that the sum of the mass of the star plus the mass of the planet is approximately equal to just the mass of the star. Adding the planet on makes almost no difference. What it also means is that the distance between the two objects, r star plus rp, is going to be about equal to rp. That's because the planet is much less massive than the star, rp has to be much more than r star, so we can approximate the sum of these two as just rp. Not quite right, but typically a planet is 1,000 times less massive than a star, so it's only going to be out by 1 part in 1,000 or 0.1%. So these are pretty useful approximations and will get us a nice answer. So given these approximations, what can we do? Well, we can look at this equation and make the approximations here on the second half of this equal to that. So what we get here is that G m planet m star over r planet squared, because it's actually r star plus r planet, but we're using this approximation up here, is pretty equal to the centripetal force on the planet, which is mp vp squared over rp. So we can cancel a bunch of stuff. The mass of the planet cancels. We can bring rp up to this side of the equation, and we end up with rp equals g m star over v planet squared. We don't know what v planet is because we don't measure the movement of the planet. What you measure is the reflex motion of the star itself. So what we know is not v planet, but maybe either the radius of motion of the star or the velocity of the star. But we do know that v planet equals 2 pi r planet over the period. That's just from working out how long it takes to go around a circle. So if we substitute that into here, we end up with r planet equals g m star p squared all over 4 pi squared r planet squared. So if you bring the r planet up to the side, we end up with r planet cubed equals g mass of the star period squared over 4 pi squared. So if we take the cube root of both sides, we get an equation for rp, which is roughly speaking how far the planet is from the star. And that's going to be equal to the cube root of all this. Neat. So that means if you work out the period with which a star is oscillating backwards and forwards, and you know the mass of the star, that's all you need to work out how far away the planet is from it. Rp being approximately equal to sum of r star plus rp. So that's given us how far out the planet is, what orbit it's in. How about the mass? Well, for that, remember that r star m star equals rp mp. We also know that the velocity of the star is equal to 2 pi r star over the period. So from this, let's say we knew the radius of the star's orbit. That tells us that the mass of the planet is just equal to the mass of the star times the orbit of the star's radius over the orbit of the planet's radius, which is about the distance we've just worked out up here, rp. So if we've got how far away the planet is and we know how far the star is moving, we can estimate the mass of the planet. Or if we knew the velocity of the star, say from Doppler effect movements, we'll be talking about that next time, we can factor into here v star equals, we've got the r of the star, it's going to be equal to 2 pi over the period. We've got r star here, which is r planet mp over m star. So it's m planet over m star times the r. So if you know the period, we can work out how far out the planet is. Once we know that, if we know either the velocity of the star or the radius of which it's motion, we can work out the mass of the planet.